let's just give him one for everything he's done. And that's pretty much what they did. Nazi Germany did not show up out of a vacuum. The anti-Semitism was already there, so, but, you know, you come up with about 3 or 4 different things, all deserving of Nobel Prizes, you can't really deny a person at least one.
And I remember that, so the anti-Semitism is what made him go to the United States.
Yeah, the extreme of Nazi Germany, yeah.
It, with good reason, and it was pretty good.
Good for us.
Yeah, well, good, yeah, good for us, probably the world, because I don't think, I would say that Hitler would have been much more fond of using the atom bomb.
Well, it would still contend the idea that if I take a uranium atom and split it apart, the mass that I end up with is less than what I started with, and that there was energy that was released in that. Experimentally, they actually had this. What Einstein's bit did was explain why it's happening.
Oh.
But Richard Rhodes wrote a book called The Atomic Bomb, or Making of the Atomic Bomb, when he says his speculation is because of the experimental evidence already that they still would have come up with a bomb even without Einstein.
Oh.
Einstein just provided okay, here's the reason why.
From what I read about him, he kind of like pieced together all these works of different physicists together. That's like my understanding of Einstein's contribution.
And the letter to the president.
Yeah.
Yeah.
Wow, that makes more sense.
I guess the letter was, you better be working on this because you're pretty sure that the Germans are doing it.
Yeah.
And the head of the German nuclear program? Heisenberg. Max Planck's son was also caught up in the whole German movement and the Nazi movement. A lot of skeletons there. All right. So Einstein makes the claim that if the energy of the photon, well, as I have it written right there, is proportional to the frequency, where h is just some constant, that means that the threshold really is the energy that is binding the electron to the atom. If you can hit it with enough energy, that the electron will pop off. So if I have a low frequency light, so we'll just take infrared. Infrared, that just doesn't.
Yeah, that's right.
That's not, okay, thank you. Let's say infrared is not enough to do it, and it hits the electron doesn't have enough energy to escape. So shining more light on it means you're just pelting it with more low energy. So all the intensity is that I'm doing more of it, but it's still low energy. So once you get above that threshold, the electron has enough energy, and so now, once we've reached that point, shining a brighter light on it of that higher frequency means I'm going to get more electrons off just because I now got more of these, and this is when photon pops in, more of these photons. But what is a photon? Yeah, there's various nebulous definitions of it, but it's a packet of energy, and you can consider it a particle if the packet is small enough. You consider it a particle.
Oh, that's a good way of describing it.
I hope so. And so we now have this evidence of light behaving like a particle. Enter quantum scattering. If I have energy coming in the form of a photon, it hits an electron, and the electron goes shooting off, I can figure out the amount of momentum I have beforehand. Now, momentum, I'll ask you, what's the formula for momentum?
Mass times velocity.
Except what's the mass of a photon?
Z. there isn't any?
Yeah. What the photon doesn't have is rest mass.
Oh,
It's moving at the speed of light.
It is moving at the speed of light. And I know that energy is equal to mc squared. So what I have here is, I don't have a mass per se in the classic sense of it, but I do have a mass equivalent. And the mass equivalent of a photon is equal to that energy, h times the frequency, divided by c squared. So if I treat that as the mass of the photon, I can now come up with a momentum. It hits the electron, it has a mass, it goes shooting off. We can assume that if the electron, the electron's zipping around the nucleus, but, close enough to at rest compared to the light that's coming in. So I have the photon coming in, the electron comes out, we can, put a detector here, we know where the electron comes. We have another detector, we can see what comes out from the light. We have a perfectly elastic collision here, or a completely elastic collision, that the light comes in, hits, and I can treat this, classic mechanics. I got two objects that come in, they smack into each other. The momentum beforehand equals the momentum afterwards. The energy beforehand equals the energy afterwards. And because some of the energy got transferred from the light to the electron, that means the light had less energy, and therefore had a smaller frequency or a larger wavelength. That's why I drew it this way. And so the Compton scattering is explained by treating photons like particles. And at this point, Newton's sitting up in his grave and said, "Told you so." But you've seen the results. We did the experiment right over here of shining light against the mirror there. We got the diffraction. We got all those great wave properties. And now the quantum people are coming in here and saying, wait a second, it's behaves like a beam of particles. So we have this wave particle duality. And physicists go, okay, yeah, we'll accept that. Behaves like a wave sometimes, behaves like a particle sometimes. Depends on how you want to look at it. And then, the Broglie comes in.
the what?
The Broglie.
Oh, the Broglie.
Yeah. I'm not sure that G is pronounced like it is in English, but I could be very wrong on that one. Never heard. The Broglie. Anyone with a decent French pronunciation?
Broglie.
There's an extra syllable in there that I don't usually. Are you claiming you have a good French accent?
If it's French, I would assume they pronounce the E. EA.
I was figuring that was one sort of,
I don't know.
Broglie.
Broglie. Try to say it wrong.
Are you gonna see if there's somebody who pronounces it right?
They
are still French.
Yeah, I'm trying to see if I can, find a way of,
I'm also seeing where they. Oh, never mind. Never mind.
There's something known as the Broglie wavelength also, so it's possible that it might show up in the dictionary. Oh, that's Wikipedia generally has a pronunciation guide. They use the International Phonetic Alphabet. Should give us at least an idea of the number of syllables.
Looking at how to pronounce the name. To quantum is in French, silent S. Usual pronunciation, it's called anything or Hawking is how it is spelled, but that's how we De Broglie, French physicist. De Broglie.
Boy.
De Broglie, French physicist. Oui, De Broglie. Louis De Broglie, French physicist.
De Broglie.
Qui en vidéo
All
That's-
So enter, see, I wrote somewhere, I wrote down his actual name. So it's longer than that one, where's the,
So we had a,
Louis Victor de Broglie, Prince de Broglie.
There you
He was royalty. He ends up being the only person to get a Nobel Prize in physics to get his Nobel Prize for his work on his doctorate. The way my physics professor at the time worded it, it was a thin little thing, about 34 pages long. My dissertation is about 200 pages long and nowhere near the impact that his was.
go. Chicken biscuit? Chicken biscuit?
Yeah, they're about 5 on the table. How'd you get comfortable with that?
What the Broglie suspects is that if light behaves like a particle and a wave, then why not particles? Can't they behave like waves? And they can. And we've talked about this before with the double slit experiment, the Davison-Germer experiment, for which Davison got the Nobel Prize. I always wondered why Germer didn't. He was just a grad student, happened to be there at the time. So as a refresher, you shoot electrons at a double slit, and what you get is, you start, and then over here, when the electron hits the wall over here, it will scintillate, and you'll get this bright dot. And what you see is, well, most of them hit in the middle, and then there's a place where none of them hit, and then it's that familiar diffraction wave pattern. And then they put a detector here, just to see which slit it was going through. And as soon as they put the detector there, the wave pattern changed into, it started behaving like a particle. You remove the detector, and you get the wave pattern. It's really strange. And they said, wait a second, all right, suppose we just send one electron through at a time. So they send one electron through, and it would show up over here. Send the next electron through, it'll show up here, next one, and you keep sending them through, and you see where the ones hit. And what you get ultimately is most of them hit in the middle, and then there's a place where none of them hit, and then you have fewer hit than none, and you basically get the pattern. So when you start dealing at this level, things start to get really strange. So the idea of the electron sort of orbiting a nucleus becomes a little less straightforward. However, I did skip the spectral line bit. I will go through that derivation.
is that the discrete spectra that you wrote about?
This is not, what I'm about to do is the discrete spectra. So let's talk about the discrete spectra. All right. I don't think I've done the routine with the discovery of the nucleus. I don't think I've done it with this group. All right, so let's talk a little bit about that, sort of give some background here. It was thought that the atom, there's what's known as the plum pudding model. Now, what they call the plum, I've always been under the impression that they called it the plum pudding model at the time. Whether they did or not, I don't know, but it's generally what it's called in textbooks now. Where it's thought that the atom was basically this, you have this fluid, for lack of a better term, you have this substance in here, which is this positively charged substance, and then the electrons are in there, sort of scattered throughout. This is the plum pudding model, and the electrons are in there like raisins in plum pudding. So if I basically have this fluid mess here with these tiny little electrons, if I sent the helium nuclei, so this is gold. So ultimately, the famous experiment, they use gold foil, and so the gold atoms, let's see, AU 79, or basically you got 100 and almost 200, what we now say. The mass of a gold atom is 50 times more massive than a helium atom. And so you send this gold atom, this helium atom into it, this helium nuclei actually, what they were calling alpha radiation. They send this into it, and what they were expecting, if the plum pudding model worked, is that basically it would go through the fluid, occasionally you get an electron knocked off, but this one, and if it got knocked an electron off, then it's moving straight, hits an electron, and then it veers slightly. This is what is expected for the plum pudding model, that the fluid in there is not going to cause it to deviate. And indeed, they get a whole bunch of stuff over here as it goes through, but occasionally, so you basically get into a dark room, you have a detector here, and you have someone who's looking through this viewer just to see if it lights up. They send an alpha particle through, and they count the number of times that this particle basically makes it into the viewer. One of the students who was doing this, one of the grad students who did this experiment was Geiger. And presumably this was this huge inspiration for, let's see if we can come up with a more automated way of detecting these things. So you're looking through the viewer, it hits, and then you move it over here, see how many hit, move it over here, see how many hit, move it over here, see how many hit. And then my suspicion is that Rutherford's suspected plum pudding model was bunk. Or they just on a whim got really lucky. They're looking at the viewer, and they eventually bring the viewer around here just to see if anything hits over here. And what they noticed, helium atom comes through, and occasionally it bounces backwards. The classic analogy would be like throwing a bowling ball in a tissue paper, and the bowling ball bounces back. With calculations and based upon the probability of things coming through, they eventually realized that there's this hard thing in the middle of an atom, what we now call the nucleus. This was turn of the century, still about the same time Planck was doing his stuff. Rutherford, probably the greatest physicist never to get a Nobel Prize in physics. He did get one in chemistry, which always seems odd to me. And 6 of his grad students ended up getting Nobel Prizes in physics.
Yeah, that is odd.
But it's Rutherford said that the fastest transformation he's ever seen in science was when he suddenly became a chemist. He didn't really consider himself. Rutherford also said that all science is either physics or stamp collecting. So I always think that's a nice thing that a Nobel Prize winner in chemistry does chemistry. You know, chemistry keeps chemists off the street, getting in trouble, keeps them out of jail. All right, so we have this nucleus here. And so the electrons seem to be sort of hovering around it. But the question is, why don't the electrons go crashing in? So here are the properties of atoms that they knew of. Number 1, atoms are very small. On the order of basically 1/10 of a nanometer. Atoms are typically stable. Atoms are typically neutral. atoms emit and absorb, not necessarily in that order, electromagnetic radiation. And what's emitted and what's absorbed is not always the same. So Bohr, who was ultimately a Nobel Prize winner in physics and also one of Rutherford's grad students, one of the several. He decided to start with the following conclusion. Now, it's usually presented, he made these conclusions, or made these speculations and then worked it out and it came out perfectly. And I suspect there was a whole lot of trial and error. This probably took the course of years and he kept tweaking it. I suspect whatever his first draft was not right. But they never talk about the first drafts. They only talk about the ones that make it. Which makes it seem like you got this brilliant people who don't work hard. They just have this moment of inspiration and boom, it all fits into place. And I doubt it just rarely works that way.
Do they have they ever, are there any records of his, first?
I suspect there are, but I don't know. I have not explored that.
I was just wondering.
All right, so Bohr proposes. So what Rutherford contributed is that there's a nucleus. Bohr now talks about the electrons. Electrons are in quantized orbits. And and as long as in that orbit, no electromagnetic radiation emitted.
What's the quantized orbit?
The quantized orbit, generally when quantized is used, that means it's discrete, it's a very specific value. So in the planetary model, I have the nucleus here.
Yeah.
I have an electron, it's gonna be going around like this. It's not like the electron is moving around and doing whatever it wants. It's in a specific orbit.
It's in a uniform orbit.
Yes, yes. Now, not necessarily, and there's various different orbits it could be in,
Yeah.
which Bohr will eventually derive.